Welcome to the JRG Cuber, the series I post videos about math in. And for this first ever episode, we'll be looking at different number bases. All number bases, in fact, for I have devised a scheme for naming every number in every base, which is called the JRG Missalian system, since it's based on Jan Miseli's a base-neutral system for naming numbering systems. A link to that video is in the description for context. The JRG Missalian system is fundamentally based on inserting numerals into the template for a positional number system. But first, let's look at the number roots that form the backbone of the system. There are roots for the natural numbers from 0 to 13, as well as 16, 17, 20, 36, and 100. Starting with the canonical forms, which are the forms of the roots take by default. 0 to 9 have their usual English names. 10 to 12 are dec, el, and do from dozenal terminology, and the rest of the roots are derived from the names of the bases of the corresponding numbers. 13 is baker from baker's dozenal. 16 is hex, 17 is sub from suboptimal, 20 is vig from vigesimal, 36 is nif from niftimal, and 100 is cent from centesimal. Next are the prefix forms, which all roots have except for 0 and 1. There's bi for 2, tri for 3, tetra for 4, penta for 5, hexa for 6, hepta for 7, octa for 8, ena for 9, deca for 10, leva for 11, doza for 12, baker for 13, testa for 16, mal for 17, icosi for 20, feta for 36, and hecto for 100. Finally, there are the suffix forms, which all roots have except for 0 to 2. There's tri for 3, quad for 4, quint for 5, sept for 7, oct for 8, nov for 9, jec for 10 from gesimal, and cur for 13 from cur's dozenal. And as for the rest of the suffix forms, they are the same as the canonical ones. Those roots I've just gone over are strung together into compound numerals according to templates listed here, with compounds themselves also having canonical, prefix, infix, and suffix forms. Wait, infix forms? The chart you shown earlier doesn't mention those. Well, for lone roots, it's simple. The infix form is the same as the prefix one, with 13 being the exception, as its infix form is the same as its suffix one. The value of a compound numeral is derived by multiplying the values of the roots together, but when constructing compound numerals, roots cannot be stuck together willy-nilly. There are rules to this. To demonstrate those rules, I'll derive the first 20 compound numerals in this system. So the first number to get a compound numeral is 14, right after baker for 13. 14 factorized as 2 times 7, so it's called bisept, with the smaller factor put first. In a similar vein, 15 is 3 times 5, so it's called triquint. 16 and 17 have single roots, so the next number that gets a compound is 18. Numbers are denoted with the two factors that are closest together. In the case of 18, that's 3 times 6, so it's tri6. Next is 19, which is prime. The compounds for primes above 17 are derived by taking the compound for the number 1 less, and prefixing on for +1, or for the prefix and infix forms, circumfixing with hen, sna. So the canonical form of 19 is on tri6, and hen trihexasna in prefix form. Where was I? 20 has its own root, so next is 21, which is trisept for 3 times 7. 22 is by L for 2 times 11. 23 is un by L, a prime, so it's 1 plus 2 times 11. 24 is tetra 6 for 4 times 6, and I'm sure you get the general gist of it by this point. By the way, you might have noticed a second ago that the word for 32 is tetraoct and not tetraoct. And that's due to the vowel coalescence rules listed here. Now, since the JRG Missalian system deals with all bases, there are compounds for numbers that are arbitrarily large, and they are unit by applying that factorization process recursively. For example, under that scheme, 98 factorizes as 7 times 14, and 14 itself factorizes as 2 times 7. What was I? So the canonical form of 98 is heptabisept. Also, it's worth noting that the factors close together rule does get occasionally bypassed when doing so minimizes the number of roots used. That's why, for example, the canonical form of 600 is hexacent and not tetrahexapentaquint. So now that we're done with how numerals are formed, it's time to plug them into the positional numeral system template. What was I? Each place value has a root for the power of the base and a multiplier prefix, although there are 3 edge cases. First, since basis 0 is always 1, the units place just has the canonical form of that place's multiplier. Second, if a multiplier is 1, that place is just the canonical form of the corresponding power of the base. And third, if a multiplier is 0, that place is just omitted entirely. Now I can fully show how the Now I can finally show how the full JRG Missalian system works in practice, and I'll use 3 pairs of random numbers as examples, with the smaller number in each pair being the base. By the way, the reason why I'm using the smaller number as the base is since if the base is equal to or larger than the number being represented in it, the result is just the number's canonical form. Anyway, let's begin with the examples, starting with 88 in base 24. 88 in base 24 is denoted as 3 times 24 plus 16, so it's called tritetra 6 hex. Next is 86 in base 7. 86 in base 7 is denoted as 49 plus 5 times 7 plus 2, so it's called heptasept pentasept 2. And the final example here is 95 in base 74. 95 in base 74 is denoted as 74 plus 21, so it's called binif trisept. And that is effectively the full JRG Missalian system explained. What the next episode of the JRG Cuber will be about and when it'll be released are both to be determined. But my next video will be the Deoda episode of Con Critic, so I'll be seeing you then.